Very often, unless something goes spectacularly, often disastrously spectacularly different from normal, the vast majority of ship histories cover the actual construction of the ship relatively briefly, saying, well, the ship was laid down on a given date, perhaps at a certain shipyard, it was launched sometime later, and commissioned somewhat later still, perhaps with some comment on the ship's trials. But what actually happens between a ship being ordered and the ship hoisting its ensign for the first time? Well, today we're going to find out, at least at a high level. Now, there's an obvious caveat here in that the procedures for smaller ships like destroyers and torpedo boats could vary, sometimes quite considerably. And of course, between navies there would also be subtle differences in build procedure, especially toward the end of the construction period, in terms of what particular order final steps might be taken in. But for today, we're going to look at, roughly speaking, how a pre-dreadnought or dreadnought battleship would have been built in a British yard. This has two bonuses. One, I've actually got fairly extensive documentation on how that was done. And two, of course, in this time period, how a ship was built in a British yard also means you get the added bonus of how Japanese ships, at least in terms of capital ships, were built in this time period, particularly the pre-dreadnought fleet, as well as various other ships, like Brazilian ships or Chilean ships or any number of other ships. So, a bit of an international flavour nonetheless. So, by the time of the pre-dreadnought, the era of secrecy was beginning to apply to all things naval, as compared to the previous centuries and even the past few decades, where on-site security to prevent sabotage might be in place, but otherwise the capabilities and size of various upcoming warships, rather than being a state secret, might well actually be the subject of quite extensive discussion in the media, as a matter of national pride, if nothing else. Additionally, since battleships had narrower margins of loading as compared to merchant ships, i.e. the difference between a battleship when empty and a battleship when loaded in terms of displacement would be far less than the difference between an empty and a fully loaded freighter, for instance. And, of course, the effect on ship's draft, top speed, and other performance characteristics was far more important for a warship. There would be much stricter scrutiny that would be applied throughout the construction process as compared to a merchant build. Now, at this point, the construction of a warship would start with a notice going out that all foreigners are forbidden from approaching the ship and, depending on the location, the shipyard during construction. Of course, if the shipyard was very large and was producing multiple civilian vessels for lots of different nations as well as warships, you couldn't forbid foreigners from the entire shipyard. But if the shipyard was building purely warships or was relatively small, then that could actually be done. If it was just the one ship, then you might have some kind of barrier or checkpoint around the area where it was being constructed and related areas, which we'll come to in a minute. There would also be the implementation of the Official Secrets Act. This had first been passed in 1889 and would subsequently be passed in various iterations throughout the 20th century, and that made the revealing of key details to third parties a specific criminal offence. Work crews would be selected, and it would be noted that all materials and equipment used in the construction of this ship were to be weighed before being installed. From those figures, you would then be able to calculate the overall weight of the ship, its approximate balance and trim, because you knew roughly where they were located within the ship, and in some cases, these weights would actually dictate in part how much the shipyard would be paid. Some items, of course, had specific prices, but others were simply priced by the pound or by the ton, depending on the scale. And speaking of scale, at this point the plans would arrive. They're usually able to be quite useful. At this point the main item of interest was a 1:48 scale plan of the hull and its lines, or 1 inch to 1 foot scale in the parlance of the time. These line plans, along with various other plans, would be taken up to a mould loft, which, despite what it might sound like to modern ears, is not in fact some small dark upper room with significant hazards to your respiratory health. It's actually an extremely large, extremely airy, and extremely well-lit vaulted area, admittedly still usually near the top of a building, hence loft, as mould, in this case, is used in the sense of thing from which you shape other thing, not strange black and white growths on the walls. In this case, each major component that needed to be fabricated, hull shell plate that needed to be hammered into shape, and each frame and beam that needed to be bent to a particular set of curves, would be translated from the plan to a full-size chalk sketch, which was made on the floor of the loft. This was done for half the ship, obviously, since ships tend to be symmetrical when looked at running bow to stern, so anything that you did for one side you could just flip over and, well, now you've got the other side as well. And each component, thus sketched, would then have a wooden template made using the chalk outline as the full-scale plan for the template. The template would then be taken away and the component fabricated to its exact dimensions and shape. This really hadn't actually changed much compared to the Age of Sail, except for the fact that the templates were used to make steel components rather than wooden ones. At the same time, the same 1:48 scale plans would be used to construct a wooden model of the ship, again just one side of it, which would turn the 2D plans into a three-dimensional object for the first time. This wooden half model would be at the same scale as the plans, 1:48, and that would then be used to work out the most efficient way to lay out the hull plates, ideally minimizing complex 3D shapes and curves for any given plate. Meanwhile, over at the Slipway, that had been pre-selected for the ship on the basis of the designer's estimates for dimensions and size, final checks would be being made on details like the exact slope of the slipway. For large ships, a ratio of around 1:19 was preferred. Significantly more, and you risked the ship launching itself midway through construction. Significantly less, and the ship might refuse to move at all. The precise angle also needed to be known to ensure that, as the frames were lowered in by crane, they could be tilted back at precisely the right amount so that they were truly perpendicular to the line of the keel, which would of course at this point usually be following the slipway. And if it wasn't, then any difference between the line of the keel and the slipway angle would also need to be noted for the same purpose of making sure the frames and so forth were aligned properly. Now, with all this done, the keel blocks could be laid out, onto which the keel plating and then the actual girder that made up the main portion of the keel could be laid. These keel blocks supported the keel some distance off the slipway, which would allow men to work underneath the ship as it took form, and also later on would provide space for the construction of the various elements of what you might term the launch cradle. Depending on the shipyard, the height of these keel blocks could vary, but somewhere in the region of 4 foot plus or minus half a foot or so was typical. Much less than this, and working conditions underneath the ship could become rather cramped, and the ship might well snag something on its way out. Significantly more, and bear in mind these are mostly timber blocks, they might have just enough play in them to make the entire structure rather unstable in bad weather, strong winds, or, if you happen to be in Japan, earthquakes. Some steel would be shaped there and then on site. Other timber moulds would be sent over to the contracted steelworks, and in some cases the shipyards had their own attached steelworks, if either they were large enough to have built them, or if one industry had been an outgrowth of another, i.e. a shipyard had decided it was going to adopt its own steelworks, or perhaps there had been a steelworks that decided to get into shipbuilding. Each piece of steel would undergo final finishing once it was on site, and it would then be covered in various markings. There would be numerical indicators showing where it went in relation to other parts, whether it was a component for the port or starboard side, and where rivet holes needed to be drilled or punched, and how large those rivet holes needed to be, as well as any other information that they thought might be useful. These steel pieces would then go into what was known as the planter's shed, which again was not full of greenery, but rather of industrial heavy-duty plant equipment. Here, pre-made parts brought in from off-site would have final trimming conducted and the rivet holes created. Punching was used for thinner plates of regular steel, as might be found in the hull shell, and thicker frames or high-tensile steel pieces would be drilled out. The steel being shaped on-site would be shaped in the planter's shed by being heated up and bent into shape as needed, but where possible, thinner plates would be shaped by cold rolling, as this was faster, cheaper, and much less complex. But of course, all of this would vary depending on what you were manufacturing and what part of the ship this was going to go on. Any markings that were still needed after this stage would then be reapplied with paint, and various small railways, sometimes human-powered, sometimes animal-powered, sometimes steam engine-powered, would be used to transport the finished steel components to the slipway, as they'd weigh a considerable amount. Here you would find many temporary derrick cranes built of timber, which would be used to move most of the individual bits of steel into place. Here and there you might also find a few larger steel cranes, although still mobile. These steel cranes would increase in number as the size of ships and thus the weight of various components rose during the 1890 to 1950 period, but however you were lifting the things, bolts would then be used to fix the steel to adjacent already in place pieces, and the riveting process could then begin. The bolts would be taken out and replaced with rivets in their turn once enough other rivets had been installed. In the pre-dreadnought period, hot rivets would usually be thrown up to men who would place them with tongs, and then they would be hammered into place manually. Usually that particular side of things would involve 3 men, one the catcher, who would place the rivet, and 2 more who would hammer it in while the catcher held the rivet in place at least until it was firmly seated. 2 men were used on the hammering for 2 reasons. Firstly, because it was faster, and secondly, the rivet would of course be cooling down, so you had something of a material time limit in any case. 2 other men usually rounded out each riveting crew. 1 man, usually a boy or an apprentice, would be heating the rivets in a portable furnace and would be responsible for chucking them up to the catcher, and the 5th man would be on the other side of whatever was being hammered, whether that be a hull plate or a frame or whatever, and he would be using some kind of heavy equipment to act as a backstop so that the rivet would shape itself on both sides at once. As time went on, pneumatic hammers would gradually replace the 2 men manually hammering, which did save a little bit on manpower, but it must be said also increased the complexity of construction, as the pneumatic hammers needed air compressors and other various bits of equipment to be nearby to power them. Towards the end of the interwar period, with the advent of the King George V class battleships, there'd also be some welding going on, but welding actually took hold, at least in British battleship construction, somewhat late compared to when it was used in destroyers and cruisers. As the basic form of the ship rose, so too would ad hoc wooden scaffolding, which was put in place to allow the work crews access to whichever bit of the ship was being worked on at the time, and could often be reconfigured in place as the ship continued to increase in size. Thus, the frames, bulkheads, plating, and decking could all be constructed, usually taking about a year or so, although again, as ships got particularly large towards the end of the period, it could take a bit longer. Large openings would then be left in various decks, which would allow the later installation of heavy equipment, such as the ship's armament and machinery. Sometimes these could be permanent openings, i.e. they'd be plated over later but specifically designed for that plating to be removed again, and sometimes that would just be an area that was to allow access to the machinery spaces, but then it would be plated over in what was hoped to be a permanent form, and then if you did for whatever reason need to get in there, it would be much more difficult to cut your way through. In any case, templates would also be taken from the relevant sections of the now completed shell plating, which would help inform the final shaping of any armour plate that would be attached to them. Also installed during this process would be certain large items that were cast or forged and could not be installed after launch. Things like rudder posts, propeller shaft brackets, the propeller shafts themselves, at least from the thrust brackets to the end, bed supports for the barbettes and the heavy propulsion machinery, and in most cases the propellers themselves and any internal armour plating that wasn't going to be able to be placed once the ship was significantly further on in the construction process. Things like transverse armour bulkheads that capped off the ends of the ship's citadel, and some of the deck armour, depending on its placement and what kind of armour scheme you were using. In some cases, elements of the ship's propulsion machinery could also be installed. To be clear, you might not install any of the ship's machinery during this stage of construction, but if you were going to be doing so, boilers are the most common item to be put in place before the ship was launched, if any, but how much of the machinery went in at this point would depend again on the size of the ship, but also particularly what kind of machinery was being used. Turbines, for example, are individually considerably smaller and lighter, and thus easier to install later on than vertical triple expansion engines. But at the same time, installing a turbine now would have less effect on the overall ship's mass compared to a much larger set of vertical triple expansion drives. What definitely was not going to be installed at this point was the superstructure, the armament, and any and all armour that could conceivably be installed in the fitting out process after launch. This means that very often, when you see pictures of battleships being launched, they'll have noticeable voids in the side where the armour would eventually go, and this often, especially around the main belt, exposes an underlying layer of teak or similar wood, which was in place as a shock absorber and spool liner in many capital ships surprisingly far into the 20th century. At this point, the ship would be approaching launch. Now for this, it needed to be tested for watertightness, because, well, if it wasn't watertight and you launched it, that was something of a rather direct and one-way trip. But, since of course the water was some distance away, you couldn't test it by preemptively submerging it. That was, of course, the whole point of launching. Instead, you'd do it by a reverse method. The outer compartments would be filled with water internally, and the exterior plating, as well as any interior bulkheads as relevant, would then be monitored for leaks. Obviously, you'd fill one compartment at a time and then drain it. If there were any leaks, you'd take whatever appropriate corrective measures were needed. And ideally, for obvious reasons, these tests would be done in dry weather. Assuming that everything had gone well, the hull could then be painted up, and the overall launch cradle could be built around it. This replaced the scaffold structures. The various components that I'm collectively calling a launch cradle would be specifically shaped to the hull in question. Now, many shipyards would keep some general-duty heavy timber frames around for multiple launches, but what would happen is they would be slid into place, and then specifically shaped timber could be attached to those frames. These components took 4 primary forms. There was a heavy timber frame at the bow, and another heavy timber frame at the stern. These were used to support the weight of these areas of the ship, as they were obviously somewhat finer and more lightly built than the central portion of the ship, once the general supports were removed. This was also quite critical because the stern, of course, would take the main force of impact when it hit the water, because that would be the first bit that hit the water. And then, as the stern began to float and the rest of the ship began to float, there would be a moment where much of the entire weight of the ship would briefly be exerting its force on the bow, as it would still be in contact with the land, and the entire hull would be pivoting around that point to gradually come to level. You would then have wooden launchways, sometimes called groundways, which would be placed along the sides of the ship between those 2 sets of heavy frameworks, and between them and the hull would be the sliding ways. Also, so you'd have some sliding ways above the launchways or groundways. The sliding ways, as the name suggests, would be heavily coated in grease and tallow, both between them and the hull, and them and the launchways or groundways. Once all this was in place, the keel blocks and other supports would be removed until the ship was resting on the slipway via these various bits of wooden framework, with very minimal friction in place, with only a couple of blocks or supports left in place which stopped the ship from moving. Thick cables or wires tied to weights, as well as heavy chains, would all be installed attached to the ship temporarily in order to provide a degree of friction as they began to pay out. This was intended to slow the ship's momentum as it hit the water. When the time came for launch, initially some very, very brave men, and later on pneumatic or hydraulic rams or some kind of tow vehicle, would pull out the couple of blocks or supports that were keeping everything in place, and the ship would begin to slide. Once it went into the water, the various timber elements that made up the launch frame would of course float free and could be recovered, but it was important that the ship coasted to a stop in relatively short order for several reasons. Firstly, because many shipyards were in rather confined waters, such as rivers, and a ship would hit the opposite bank long before it lost momentum if you didn't have those drag chains attached. Secondly, even if you were launching into an area with much more open water, like a harbour, and thus a longer run-out could be allowed for, you've got to remember this hull is mechanically dead. It has no power, no steering. It's just a dead weight. And of course, areas of more open water, like harbours, usually mean there's some form of active shipping going on. So since the hull has to be retrieved by tugs and taken to wherever it is you want it to go, the very last thing you want was a half-built battleship barrelling out into, say, Portsmouth Harbour, merrily carrying on to smash up some of the local shipping, and then gently drifting away on the current or the tide before the bewildered tugs could catch up, because, let me tell you this much, no tug is going to be directly behind a battleship that's in the process of launching, not if they value their lives. It was therefore also important to regulate just how much tallow, grease, or other lubricant was being used, both in terms of type, as certain types had different freezing temperatures, and the last thing you wanted was the whole thing frozen to the blocks if the weather happened to be especially cold, but also in terms of sheer amount, something that USS New Jersey would find out to her cost when somebody was just a little too generous with the lard when she was being launched. Once the hull was in the water and under the tug's control, the chains and wires that had been used to provide ground anchorage could be disconnected, and the ship could then be taken for fitting out. Now, in the UK, prior to 1904, this could only be done, at least by decree, at a royal dockyard. This, to be honest, was something of a holdover from the period when the government was a little nervous about private companies having access to large amounts of heavy artillery, but by 1903-1904, so much construction was taking place, and bearing in mind that the royal dockyards were also in the process of building ships themselves, that there was a huge backlog of half-completed ships waiting for fitting-out berths to become available. Now, that obviously wasn't ideal, and then somebody worked out that while seizing and repurposing a few hundred 18, 24, 32-pounder cannon was relatively easy for someone who was feeling particularly rebellious or was going to conduct a big raid, a 12-inch gun that weighed dozens of tons and needed highly specialised loading and elevation mechanisms to actually function was essentially a useless cylinder of metal on its own. Plus, it was also costing a fair bit to pay for the insurance and the towing ships that were needed to move incomplete ship hulls safely up and down the UK coast to the Royal Dockyards. And so, since it was obviously quicker, faster, cheaper and safer to just do the fitting out at the building yard, if said yard was equipped for it, ships would now mostly be fitted out at the yard they were actually built at. The fundamental process, though, didn't change all that much, except that there wasn't a rather dangerous voyage in between. It should also be noted, I think, that another reason why the Royal Dockyards were supposed to be the only place you could fit out a ship was a degree of protectionism, in that during periods of leaner funding, if you had to have work done at the Royal Dockyards, at least in part, it meant those dockyards could keep active and keep a trained workforce. By the late 19th century and the beginning of the 20th century, however, workload was not a problem. The fitting out process now took two primary forms, which I shall term the general fitting out process and the heavy fitting out process, although in period terms it's just fitting out. So general fitting out involves swarms of workmen installing the ship's internal fixtures and fittings, sometimes lightweight bulkheads, dividing up larger compartments like accommodation areas, installing basic furniture, the plumbing, the electrics, various doors and hatches beyond the minimum necessary to keep the ship watertight, laying down the wooden decks for areas that needed wood or latterly linoleum decking, installing the galley equipment, the ventilation fans and ducts, the machine tools for the ship's workshop, anchors, chains, cables, boats, derricks, small cranes, etc., and things like this. All of that was generally done by muscle power alone and occasionally assisted by some small cranes. And then you had the heavy fitting out. This was the stuff you needed the really big cranes for. This would start up with the installation of any and all heavy machinery that hadn't been installed during the build phase. Boilers, engines, backup generators, steering motors, all the pipework to connect it, and of course pumps to move the boiler water to the boilers. All of that had to be dropped in through the gaps that had been left in the deck plating. Then those gaps could be sealed up. And then would come the construction of the superstructure, the bridge, the funnels, the installation of the conning tower, the stepping in of the masts, and things like that. Much of that would obviously need to be brought in by heavy lift crane, and had to be done in a rather specific order so as to maintain the overall balance and trim of the ship. While all of that was going on in roughly the amidships area, there would also be the installation of the secondary armament, which would start just before the major central superstructure elements were installed. If the secondary battery was the older style in casemates, both they and their ammunition hoists would usually be in place before major superstructure work really got underway, as the upper deck would need plating up to allow the workers to install the various upper works, and of course for the teak decking to go down, and all of that was above the level of the casemates. In later ships, the ammunition hoists, and occasionally barbettes where applicable, could be put into place early on, but the final installation of the guns and their turrets would be done after most of the superstructure work, since the secondary guns were both above the upper deck, so there was no problem with plating in that section of the ship, and they could potentially get in the way of work being done on the superstructure if they were installed first, simply by just being there. The final really big job would of course be the installation of the ship's main battery. The barbette would be lowered into place in sections. Again, some elements of this might have been installed during construction on the Slipway, but not always, and where this was done it was usually just the outer shell, not including the heavy armour plates. Once this was in place, the ammunition hoists, the roller path, and other systems could be installed. The roller path, or specifically the bulkheads that supported it, were especially complex, and it was an incredibly delicate procedure because, amongst other things, a giant levelling router, or router, depending on your accent, or planing device, depending on if you want to be technical or not, would have to be craned down in to the barbette to machine this part of the gun battery absolutely perfectly level and smooth, which of course also meant the ship needed to be both in trim and stationary, because not only did the turret need to be on a perfectly level surface to rotate properly, but that surface had to be in alignment with each other main battery turret, the fire control system rangefinder base, and the central datum point from which all the calculations for fire control would be referenced. Once that was done, the bearing path could be laid, and the base of the turret could then be inserted on top of it. If you got that wrong, you'd have at best uneven turret rotation, which would have rather negative effects on your gunnery, as well as the balance of the ship, and some rather worrying power fluctuations in the driving machinery, and if you got it really badly wrong, the turret wouldn't turn at all. Once the base of the turret was installed and confirmed that yes, it was in fact rotating smoothly, the main guns could be brought in, and of course the gun mountings also had to be put in place, and all of this was usually done while the turret sides were in the process of being built up. Any other large equipment that went in the turret, like rangefinders, basically anything that couldn't fit through a hatchway, would also be installed at this point, and then the turret roof plates would be installed and locked into place. These would be bolted in such that they could be relatively easily removed and then lifted off when the guns needed replacing. It should also be noted that the gun turrets themselves would have been assembled, tested and checked in the gun pits at the gun foundry before then being disassembled, partially assembled and rechecked in the dockyard, and then disassembled again and finally checked once they'd actually been installed. At all stages of fitting out, various bits of equipment would be being tested, tuned, and then retested or fixed as necessary at the time of installation, and potentially several more times if they could be run set and checked separately, but also happened to be part of a larger system, which in and of itself might need to be checked once other components had been installed. For example, a capstan motor could be tested to see if it would run at all the minute you'd installed it. But then you might run it once the capstan cylinder was installed to check the connections between the two and make sure the cylinder was rotating freely. And then once the chain and the anchor were attached and hooked up to the capstan, then you might test the whole system. And then you might test it again during exercises involving multiple anchoring sections all going at once. Then, finally, it was time to bring the ship to life. The machinery trials could vary somewhat depending on the ship and the manufacturer, but the core trials, assuming that the ship wasn't going to be rushed ASAP to the front lines, would consist of 6 separate items as follows. Firstly, a basin trial would involve firing up the machinery while the ship was still moored alongside, just to check that everything was working and nothing was going to explode immediately. Second, you would have the first sea trial. This tested out pretty much everything and made sure it worked, at least to some degree, and got the ship underway. The ship would then be run at various power levels, which would include a brief run at full power. Third would be a 30-hour-long endurance trial where the ship was taken up to its planned cruising speed and then left there for pretty much the entire trial. This would allow a detailed assessment of the ship's fuel consumption and therefore its overall range as compared to the figures planned for, as well as allowing an assessment of whether or not the planned revolutions per minute for given speeds were actually accurate and if any adjustments needed to be made. Fourth would be measured mile runs. This would involve a ship then setting itself at various power levels, half ahead, cruising, and full power, as well as overload, and then entering a measured mile patch of sea once they were comfortably at that level, so they'd start their run up some miles before. The time from when they passed the starting buoy to the finish buoy could then be used to give the ship speed, and the ship would then have to come around and make the run in the opposite direction, with an average between the two taken, which would account for possible effects of wind and tide. Fifth would be a full power trial, where the ship would be run for 8 hours at full power in order to make sure that nothing broke during an extended high-speed run. And sixth would be the acceptance trial. This would be a final run, which included a full power run, and ended with the Admiralty formally accepting the ship into its service. This might be a lap out and back to its berth, or it might leave its berth and head over to a Navy base where the ship would then remain for the first part of its active service, depending on circumstances. Various other minor trials, such as running up the auxiliary machinery, running on the auxiliary machinery, running the ship in reverse, and other such things, would be interspersed with the main trials, and this whole procedure could take several months, as after each voyage, the responsibility for fixing any faults, breakages, or just fine-tuning things was still the responsibility of the shipyard that built the vessel, and if they didn't put a vessel forward that actually worked, there would be significant penalties. Now, unlike destroyers, which usually had a mandated minimum speed requirement as part of their design regimen, battleships were generally built much more closely and precisely to the specifications of the Admiralty plans, whereas essentially the smaller the ship was, the more freedom the shipyard had to interpret the plans. It was assumed that with capital ships, the Admiralty had therefore made all the weight, power, and hull form calculations correctly, and thus the builder usually only needed to show that the ship was in fact putting out the required specified power. As long as the requisite power was going to the propellers, then any variation in speed from the design speed, unless the ship was noticeably overbuilt or poorly trimmed as compared to the design specs, was the Navy's problem. Or potentially the benefit, depending on if the ship, of course, was faster or slower compared to its target speed. This is one of the more noticeable areas where Royal Navy practice varied somewhat from other nations, as in many other navies, a builder might have payments, bonuses, or penalties associated with how much faster or slower a capital ship moved compared to the design speed, which does go a long way to explaining the rather specially engineered circumstances of some ships' trials, particularly for the Imperial German Navy's battle cruisers, and to a certain extent the Regia Mariner's capital ships as well. Once all these basic trials had been done, the ship would be accepted into naval service, commissioned, and then enter the fleet for further working up and trials. This would involve further machinery test runs, gunnery practice, and things like that, but usually this was more to get the new crew used to operating the ship, as opposed to verifying that the ship worked in the first place. Now, of course, in times of war you might have severely shortened or even skipped trial phases, perhaps also with the crew coming aboard a lot sooner during the fitting out process. And even in peacetime, Some trials that would typically be done after commission could end up being done before commission, especially when it came to experimental vessels. But broadly speaking, what we've just discussed is a reasonably high-level run-through of the typical build, fit-out and commission sequence for a large warship built in British yards between 1890 and 1950. And if you haven't already, I would strongly recommend picking up a copy of The Battleship Builders by Ian Johnston and Ian Buxton, if this video has been of any interest to you, as that book goes into immensely more detail on this and the many other processes involved in the design, construction and commissioning of capital ships in this time period.
That's it for this video. Thanks for watching. If you have a comment or suggestion for a ship to review, let us know in the comments below. Don't forget to comment on the pinned post for dry dock questions.